Hello and welcome back to the Science of Concrete Materials class. This is lecture number 24 of the class, and today we will continue our discussion on the aggregates module. Last lecture we stopped on the size gradation, the grading curves. Previously we discussed the shape and texture, their impact on workability and mechanical properties. We also talked about the size gradation, basically size grading. We talked about size analysis. We talked about the maximum aggregate size and its effect on the voids, which is basically the paste requirement, and its impact on the strength as well. Today we will continue our discussion on the grading curves. Basically, when a sieve analysis has been completed, according to the provisions of ASTM C136, the weight of the aggregates retained on each sieve is expressed as a percentage of the total weight of the sample. This is then used to calculate basically the cumulative percentage retained on each successive sieve, or the cumulative percentage passing each sieve, as I will show on the next slide momentarily. These numbers can be plotted graphically against the sieve size, as I will show again on the figure, to give us the grading curve. It is customary to use cumulative percentage passing on the ordinate. The successive standard sieve size are plotted linearly on the abscissa, as you can see here, okay, on this curve right here. Okay, this is effectively gives a semi-log plot, since each sieve size is related by a factor of 2. So therefore, the half sizes should be placed between the other sizes, as is correct for logarithmic scales. The ASTM C33 sets grading limits for fine and coarse aggregate based on practical experience. So these limits are also summarized on the table right here. Okay, for fine aggregate this table is, and after that I will show another one for coarse aggregates here. Okay, these are shown here for various nominal sizes. If an aggregate basically does not conform to ASTM C33 grading limits, it does not necessarily mean that concrete cannot be made with these aggregates. It does mean that the concrete may require more paste, and maybe it will be more liable to aggregate segregation during handling and placing. That's what it means. So it is easiest to maintain uniformity of concrete if the aggregate grading remains constant. On large jobs, where considerable quantities of concrete, will be required, it may be advantageous to blend several fractions of coarse aggregates, to maintain uniformity of grading. This is, a common procedure in ready-mixed concrete plants, since concrete can be produced more economically when corrections of the grading, variability are eliminated. So the key is you want to maintain uniformity. Okay, that's the key, uniformity. Okay, so basically here's the table I was talking about. It can't be seen that quite wide grading limits are provided, which allows for adjustment for differences in aggregate shape and texture. Okay, So here, for example, this is, as I said, this is the ASTM grading limits for fine aggregates. As you can see, these are the sieve sizes, the nominal sizes and the number, the sieve number. We talked about these before. And here are the recommended passing percentages of the aggregate, okay? This is here basically grading curves, indicating the specified limits, for ASTM C33 for fine aggregates and for one size of coarse aggregate, as you can see here. There is also a combined grading curve where 40% aggregate, fine aggregates, and 60% coarse aggregate. This is for the mid-range of ASTM limits, as you can see here. Okay, and this is the corresponding Fuller-Thompson basically ideal grading curve shown here. Okay, so as I said, the aggregate size is indicated on the abscissa and the percent passing on the ordinate. And again, what we said here, if the aggregates do not conform to ASTM C33, it does not mean they cannot be used to make concrete. It's just you will anticipate problems because these were established, based on experience and what works better. So again, the second thing is the key is to maintain uniformity to avoid justification and corrections to your mixed design, because it is basically made with a certain grading, and every time the grading changes you have to make adjustments. Okay, so uniformity is key. Here is the ASTM grading limits for coarse aggregates, as you can see here, for the various sizes. For example, what would you specify? Number 67 rock size, which is 19 millimeter, 3/4 of an inch. These are the passing of each sieve in order to meet the ASTM limits. If you are using 57 rock as a maximum size, these will be the passing limits, and so forth and so on. Okay. Okay, so speaking of the uniformity of the aggregates, the use of a single parameter to describe the grading curve can be useful in checking the uniformity of a grading. The fineness modulus is such a parameter. It is defined, as basically shown in equation number 1 here, which is the summation of the cumulative percent retained on standard sieves divided by 100. Where basically the standard sieves used are, the 150 micrometer number 100, the 300 micrometer number 50, the 600 micrometer number 30, the 1.18 millimeter number 16, 2.36 millimeter number 8, and the 4.75 millimeter number 4, the 9.5 millimeter, the 3/8 of an inch, 19 millimeter, 3/4, 37.5 millimeter, the 1.5 inch, and larger, increase in the size ratio 2:1. Okay. The fineness modulus is usually calculated only for the fine aggregates, but may be calculated for the coarse aggregate as well, based on the assumption that the 100% is retained on each of the sieves from 1.18 millimeter, the number 16, to the 150 micrometers, which is the number 100. So the fineness modulus for the coarse aggregate becomes as defined in this equation, labeled as 1A, which is the summation of the cumulative percent retained on standard sieves, including 2.36 millimeter plus 400 divided by 100. Okay. So the fineness modulus for fine aggregate should lie between 2.3 and 3.1. Okay. as shown in this sample calculations here. So a small number, indicates a fine grading, whereas a large number indicates coarse material. So the fineness modulus can be used to check the constancy of grading when relatively small changes are to be expected, okay? But it should not be used to compare the grading aggregates through two different sources. Again, we check it for uniformity of one source, okay? The parameter also, as can be construed, it's a quite crude measure of grading. Two aggregates with the same fineness modulus can have quite different grading curves. So again, it's not really any indication other than for the uniformity and the constancy of grading when we are expecting basically small changes or variations from a certain source of aggregates, okay? So here's what I said, it shows here the calculations for fine and coarse aggregates of the values of the fineness modulus, okay? As you can see, I said it's between 2.3 and 3.1. Here it is 2.59, and here's for the coarse aggregate. But like I said, this value here is basically not much use. Okay. Okay, the fineness modulus of fine aggregate is required for mixed proportioning. Basically, since sand gradation has the largest effect on workability. So the finer the sand, the lower fineness modulus, the greater the number of particles available to improve workability. This may allow an increase in the amount of coarse aggregate, and a decrease in the amount of fine aggregate in the concrete. Okay, once we know more about it. The ASTM C33 requires that the fineness modulus does not vary by more than 0.2 from the value used for a design, for a mixed design purposes. So larger variations will cause unacceptable changes in workability and may require or will require reproportioning. Okay, so basically, to maintain, you base your calculations based on a certain fineness modulus from a certain grading of aggregates, and that's where you base your mixed design upon. If the value varies by more than 0.2 as indicated, there will be some recalculations. As I said, the fineness modulus of coarse aggregate is not used for mixed design purposes. Okay. Okay, so let's look at the other grading requirements, and we looked at these, gradation curves, and we saw how useful they are in maintaining uniformity and for performing mixed design. There are some other grading requirements. So the ASTM specifications, permit a wide range of grading, as we have seen a few slides ago. Particularly in the case of fine aggregates. Other specifications may require much narrower limits, depending on whether, rounded gravel and sands or granular crushed rock and manufactured sands are available, depending. So the amount of fine aggregate passing the 300 micrometers, number 50 sieve, and the 150 micrometer, number 100, passing these sieves, affects workability, finishability, bleeding, and so on. So an adequate fine material is needed for good cohesiveness and plasticity. Remember that. So the 10%, passing the 300 micrometer, the number 50 sieve, allowed by ASTM may not provide sufficient fines, for hand finished concrete floors, or when a smooth surface texture is required. In such cases, it is recommended that fine aggregates should be used that at least 15% passing the 300 micrometer, number 50 sieve, and 3% or more passing the number 150, number 100, which is 150 micrometers. On the other hand, ASTM C33 allows, the finer fractions to be reduced or omitted if the concrete contains certain workability aids, such as a mineral admixture or an air entraining agent or high cement content. But the ASTM limits the very fine fraction passing the 75 micrometer number 200 mesh sieve to not more than 5% for most concretes, and 3% if the concrete is subject to abrasion. And again, the finer the aggregate, it will be less resistance to abrasion. So the reason, as I said, is that the material often referred to as fines result in a very high water demand due to its high surface area, and because it takes the place of cement particles on the upper surface of concrete, reducing abrasion resistance. So in natural aggregates, fines are likely to be rich in clayey matter, which may increase the volume instability of the concrete. So again, ASTM, does not impose limits. However, certain precautions need to be taken, okay? So the grading requirements of the fine and coarse aggregates in the ASTM C33 do not, in themselves basically guarantee the concrete will have the desired properties, as we will see in coming up lessons. So recommendations, dating back for many, many years, address the grading or the gradation of the combined aggregates based on that. So the principal goal was to obtain a dense gradation producing low void content and a resulting minimum cement requirement. And again, when it comes really to gradation, much room for improvement is still there. And again, experience and experiments will go a long way in determining, or proposing the best combination of aggregates. So in practice, this approach, cannot be used, what I just mentioned, because, the resulting concrete has an adequate workability. So, this does not mean, that consideration of combined gradation is without use. For example, combined aggregate gradations can be used to optimize workability, economy, and strength, as we have seen before. So let's look at some other grading methods. We're talking about, the key here, we're talking about, the combination, the limits to allow flexibility, because, sources of aggregates are really running scarce in many locales. So basically, there is a flexibility offered by the ASTM limits. And again, the AST limits are not really engraved in stone. However, wherever you deviate from these limits, you have to justify by solid proof, like experiments or research results, that what you are proposing will definitely fit the purpose in terms of workability of concrete, and most importantly, durability of concrete eventually. Of course, economy not to be discounted as well. Okay, so as I said, let's look at other more grading methods available. There's something called gap grading. Gap grading is defined as grading in which one or more intermediate size fractions are omitted. As you can see in this one, I showed this before, but I'm showing it here again for reference. Okay, so gap grading can be used to produce more economical concrete, in particular when blending of aggregates is required to obtain suitable gradings. As I said, you may not always have the luxury in some locales of the availability of all aggregates to have a uniform grading. So sometimes you end up, combining different aggregates in order to produce, some economical concrete. basically less sand can be used for a given workability, and thus, allowing the use of less cement or lower water cement ratio for a given slump. So like I said, you could be creative when it comes to gradation, but you must know what you're doing. Also, the omission of size fractions may lead to severe segregation problems, particularly in mixes of high workability. So again, we're talking about workability, economy, and durability. Okay? So the gap grading is recommended primarily for stiff mixes of very low workability that are to be compacted by vibration. Usually close control of mix proportions, must be maintained to avoid segregation. So it does not, appear that gap graded concretes are inherently superior to continuous graded concrete. Okay, but claims of improved properties, in this case, can be attributed to decrease in the water cement ratio, because I said we can have higher workability, lower the water cement ratio for a certain given workability. So decrease in the water cement ratio at a given cement content and slump. The gap graded aggregate is often a gradation method is often used to give better exposed aggregate finishes. So that one particular use. Okay, so a special case of the gap grading is the no fines concrete, in which the fine aggregate is entirely omitted, as you can see in this figure here. So, as would be expected, this concrete has little cohesiveness in the fresh state and cannot be compacted to avoid free condition for obvious reasons. Consequently, the no fines concrete is a low strength, high permeability material in which coarse aggregate, lightly compacted by gravity or by light riding, is cemented together by paste rather than mortar, but without completely filling the voids between the aggregates. So the advantages of the no fine concrete are its low density, low drying shrinkage, and high thermal insulation, which can be used when structural requirements are not very high. Okay. So, let's continue with the properties of the aggregates required for mixed proportion. The third property is the moisture content. Okay, since aggregates contain some porosity, water can be absorbed into the body of the particles. And also, water can be retained on the surface of the particle as a film of moisture. That means, stockpiled aggregates can have a variable moisture content. It is necessary to have information about the moisture content, since if there is a tendency of for the aggregates to absorb water, it will be removed from the paste, so the water cement ratio is effectively lowered and the workability of the concrete is eventually decreased. On the other hand, if excess water is present at the aggregate surface, extra water will be added to the paste and the water cement ratio of the concrete will be higher than desired. So knowing the moisture content is extremely important. So there are 4 moisture states, it is convenient, to define the moisture states of the aggregate, in these 4 states. I will show them schematically here, but let's talk about them. First one is the oven dry, abbreviated as OD. In this case, all moisture is removed from the aggregate by heating in an oven at 105 degrees Celsius to constant weight. Basically, if you in a lab, you will do this, overnight heating, and that will be enough. All pores are empty. We have the second state is the air dry, abbreviated as AD. Remember, these abbreviations and these terms because you're going to need them when we do the mix design. Very important. The AD, air dry, all moisture is removed from the surface, but internal pores are partially full. The third one is the saturated surface dry, SSD. All pores are filled with water, but there is no film of water on the surface. The fourth state is wet, which basically all pores are completely filled with water with a film of water on the surface. Okay, so of these four states, only two, the OD and the SSD states, correspond to specific moisture contents, and either of these states can be used as a reference state for calculating moisture content. You know, the AD and what states represent the variable moisture content that will exist in a stockpiled aggregate. Okay, so the SSD condition basically is a better choice as a reference for the following reasons. First, it represents the equilibrium moisture state of the aggregate in concrete. That is, you know, the aggregate will neither absorb water nor give up water to the paste. Second, the moisture content of aggregates in the field is much closer to the SSD state than the OD state. Third, the bulk specific gravity of aggregates is more accurately determined by the displacement method in the SSD condition. The fourth reason, the moisture content can be calculated directly from measurements of apparent bulk specific gravity using displacement methods. You know, the bulk specific gravity and the apparent specific gravity, those terms we will talk about in detail in this next or maybe the following lecture. Okay, so a major disadvantage, you know, speaking of the advantages of using the SSD, a major disadvantage of using the SSD state is that it is not easy to obtain a true SSD condition, and basically it requires skill and practice to do so. Many people, though, prefer to use the OD state as a reference point because of this difficult determination of when you reach that condition. In the rest of the discussion, we will use the SSD as the reference state. But as I said, in a coming up lecture, maybe the next lecture or a following lecture, where I will have a lecture basically dedicated to certain calculations of these terms, I will show also a set of calculations where the OD state is used as a reference. Okay. Here is these four states I just mentioned. Here is the oven dry state, air dry state, saturated surface dry, the wet state. And it shows, again, here there's this term called absorption capacity, and there is an effective absorption from this state to this state, surface moisture. Remember these because we are going to use them, and they are very important, as I said, in the mix design procedure. You must know all these things, and you must calculate them accurately because they're going to impact your water cement ratio and so on. Okay, so let's talk about the absorption and surface moisture. To calculate the amount of water that aggregate will add or subtract from the paste, it is convenient to define these three quantities. 1, 2, 3, the one I just mentioned. Basically, absorption capacity, effective absorption, and surface moisture. Okay, the absorption capacity, referred to as A, or absorption, represents the maximum amount of water the aggregate can absorb. Basically, it's calculated from the difference in weight between the SSD and the OD states, you know, expressed as a percentage of the OD weight, as you can see here. In this equation, and we refer to this equation as equation 2. Remember these numbers, keep track of them, because I'm going to keep going and we will refer back to these numbers when needed. Okay, so basically, as we said, where is the WSSD is the the weight of the aggregate in SSD, and WOD is the weight of the aggregate in the OD state. Okay. So the absorption capacity is used in mixed proportioning calculations and can be used to convert, from SSD to OD system or vice versa. So that's the convenience. Most normal weight aggregates, the fine and coarse, have absorption capacities in the range of 1 to 2%. Abnormally high absorption capacities basically indicate high porosity aggregates, which may have potential durability problems. Like the lightweight aggregates generally have very high absorption capacity. So from the absorption capacity, you could sometimes get an indication about the quality and the suitability of the aggregates. Okay, the effective absorption, EA. The effective absorption represents the amount of water required to bring an aggregate from the AD, air dry, to the SSD state, expressed as a fraction of the SSD weight, as you can see in this equation number 3, which is EA equals the WSSD minus WAD over WSSD. Basically, for a required, and we defined this is the weight of the aggregate in SSD, this is the weight in the aggregate of the aggregate in the AD. For a required weight of SSD aggregate in a concrete mix, let's say, weight of aggregate, denoted by weight of aggregate, the effective absorption can be used to calculate the weight of the absorbed water. Again, preferred water absorbed to bring air dry aggregate to the SSD, as you can see in this equation, basically number 4. So the weight of air dry aggregate batched will equal the desired weight of SSD aggregate, the weight of the aggregate, minus the water absorbed, while the mixed water will be increased by the water absorbed, the weight of the water absorbed. Okay, keep track of all these. So if an aggregate is close to the oven dry condition when batched, it takes the aggregate some time to absorb all of the water necessary to reach the SSD condition. You have to keep that in mind. Think about it. So in such cases, the effective absorption may be taken to indicate the amount of water the aggregate absorbed in 30 minutes, because you cannot go indefinitely. I mean, this process will not stop, but mostly done in 30 minutes. Although, further absorption beyond this time will be slow, but this absorption will be accompanied by a gradual decrease in workability of the concrete, because absorption will go on. Although small, you may experience some loss of workability or decrease in workability. Okay, let's keep going. We have the other parameter, which is the surface moisture. This represents water in excess of the SSD state, also expressed as a fraction of the SSD weight, as you can see in this equation number 5. All right, so basically it's equals the wet weight minus the SSD weight divided by the wet weight multiplied by 100%. All right, it is used to calculate the additional water added to the concrete with the aggregate. Okay, so the added water here equals to the surface moisture multiplied by the weight of the aggregate divided by 100%. This is equation number 6. So in this case, the weight of wet aggregate, will equal the weight of the aggregate plus the weight of the added water, while the mixed water will be decreased by an amount equal to the water added, calculated from equation number 6, to account for the surface moisture, which basically it will affect the water cement ratio, as I mentioned. So basically, as I said, keep track of all these because they will come in handy when we do the mix design. Okay, so equations number 3 through equation number 6, can be put in general terms, since both the AD, the air dry weight, and the wet states represent basically the possible conditions of the stockpiled aggregate. The moisture content denoted as MC okay, here shown on this slide. The moisture content of the aggregate is given by this equation, number 7. As you can see, the weight, the stock pile weight minus the SSD weight divided by the SSD weight multiplied by 100%. It's equation 7. Okay, so where, as I indicated, the weight W stock is the weight of the aggregate in the stockpiled condition. So if the moisture content is positive, it is surface moisture. If it is negative, it's effective absorption. So you have to keep in mind. So the weight, the moisture content equals the MC times the weight of the aggregate over 100%. Equation number 8, where basically the WMC is the total moisture associated with the aggregate, and it is positive, mean added when the moisture content is positive, and negative mean absorbed when the moisture content is basically negative. Okay, so there is another term I would like to introduce here called the bulking of sand. Okay, the stockpiled coarse aggregate is generally in the AD state, with an effective absorption of less than 1%. However, fine aggregate is often in the wet state, with the surface moisture typically in the range of 2 to 6%. So the presence of the moisture has a beneficial effect because it limits segregation of the fine aggregates. The reason, for the high moisture values of the fine aggregate is that in addition to thin surface films of moisture, additional water can be held in the interspace between the fine particles, as a result of the formation of what's called the meniscus. All right. So the formation of this meniscus creates a thicker films of water between the aggregate particles, pushing them apart and increasing the apparent volume of the aggregate. This phenomenon is known as bulking and can cause substantial errors in proportion and by volume. Okay, when we come to the mixed proportion, and we're gonna see two methods, one by volume, one by weight, and you're gonna make more sense of this. Because of this, though, aggregate is nearly always batched by weight, and measurements of unit weights, are usually made on the oven dry aggregate. All right. So when sand is saturated with water, the meniscus are destroyed and the volume returns to normal. So coarse aggregates, show much less bulking, since the particle size basically is large compared to the thickness of the water film, and the effective meniscus formation is basically very slight. All right. So here is this concept of bulking. As you can see here, we have the three states. A is the dry, B partially saturated, we have meniscus formation, and we have the fully saturated. Here, the graph here in D, in figure D, shows an increase in the volume as a function of surface moisture. As you can see, this is the A, surface moisture, And this is the B situation, basically. In this case, is the highest volume. And this is the C. This is for coarse and fine. For fine is much more evident than it is for coarse aggregate. And again, this is important when you do mixed proportion and by volume, but nonetheless, you need to be aware of that. Okay, so let's talk about specific gravity. So the density of aggregates is required in mixed proportion to establish weight-volume relationships. The density is expressed as the specific gravity, which is a dimensionless ratio relating the density of aggregate to the density of water, as you can see in this equation number 9. So density of solid, density over density of water multiplied by 100%. Okay, since densities are determined by displacement in water, specific gravities are naturally and easily calculated and can be used with any system of units. Easy. But it must be remembered that aggregate contain some porosity, and the specific gravity value depends on whether the pores are included in the measurement or not. So it is also necessary to distinguish between pores that connect to the surface of the aggregate, particles, maybe basically permeable pores, and the pores that are sealed within the particles, impermeable pores. For the purpose of this discussion, the impermeable pores will be considered as part of the solid. Okay, so we have to distinguish between the apparent specific gravity, ASG, and basically the bulk specific gravity, BSG referred to, and based on oven dry condition and SSD saturated surface dry condition, these values. Don't worry, I will have another lecture about all these calculations and equations. So just be familiar with these terms, and we will look at how we determine these in a coming up lecture. Okay. So this referred to as equation, the apparent specific gravity larger than the bulk specific gravity in SSD, which is larger than bulk specific gravity in the OD condition. Okay, this is equation number 12. I know 10 and 11 are missing. I will talk about them later. But as we said, since the porosity of most rocks is used in concrete is 1 to 2%, the values of all specific gravities are approximately the same, in the range of 2.5 to 2.8. But you must know all these terminology and how we calculate them. Okay. Okay, so let's move on to the next term, which is the unit weight. Okay, the unit weight, or abbreviated as UW, or bulk density, is the weight of a given volume of graded aggregate. So it is basically a density measurement and is also known as bulk density. But this alternative term is similar to bulk specific gravity, which is quite different quantity and perhaps is not a good choice. All right. So the unit weight effectively measures the volume that the graded aggregate will occupy in concrete and includes both solid aggregate particles and the voids between them. So the unit weight is simply measured by filling a container of known volume and weighing it according to ASTM 29, I believe. So clearly, the degree of compaction will change the amount of void space and eventually the value of the unit weight. Okay, so the ASTM standard method calls for compaction by rodding, and the unit weight of the lightweight aggregate is often determined in a loosely packed condition without compaction. So since the weight of the aggregate is dependent on the moisture content of the aggregate, a constant moisture content is required. Oven dry aggregate is used in the ASTM C29. Okay, so the maximum unit weight of a blend of two aggregates, is about 40% fine aggregate by weight, and 60%, of course, will be coarse aggregate. So this is the most economical concrete aggregate, since it will require the least amount of cement. Okay, so the unit weight of both fine and coarse normal weight aggregates, fallen within the ASTM grading limits, are generally in the range of 1450 to 1750 kilograms per cubic meter, or 90 to 110 pounds per cubic foot. Okay, unit weight is also the most common classification of aggregates, as we mentioned at the beginning of this module about normal weight, lightweight, and heavyweight aggregates. So this classification is very common. Okay, this is the graph I mentioned in the previous slide. If we go back to the previous slide, as I said, the maximum unit weight of a blend of two aggregates is about 40% fine aggregate by weight. So, and we said this is the most economical concrete, since it will require the least amount of cement. Basically, we're talking about the voids will be less, you require less cement paste. But again, I will keep mentioning, we have a compromise between workability, economy, of course, strength I'm not worried too much about, because we can achieve it. I'm worried about durability and workability, basically. Durability for long-term performance, workability for handling. You have to feel for these guys who are handling the concrete. If you want them to give you good, well compacted, finished concrete, of course, you have to provide coaching, supervision, but also make their life easier by providing the most appropriate mix in terms of handling. Okay, so back to this graph. As you can see, this is here a variation of the unit weight of dry rotted aggregate, for blends of fine and coarse aggregate, and here's the unit weight. So basically, the most economical being roughly 40% fine aggregates. Okay, we will visit this curve again, and we will visit the unit weight and the bulk unit weight and all the other terms I mentioned basically when in the lecture following the next lecture, when I talk about those calculations lecture. Basically, I'm going to have about all these terms. Okay, so by this we finish the properties of the aggregates required for the mix design. Next lecture, though, we will talk about the durability of aggregates. Until then, thank you for watching, and I will see you next time. Thanks.